It's for all your fans online.
Oh, no, I just want to ask a follow-up question, which is, all right, and since you're at University of Central Florida, I'll ask you something that Dan Britt told me the other night. So we were talking
I'm not
about.
responsible for what Dan Britt tells you at night.
I understand.
Okay.
But
Just making sure.
this way you can continue this argument with him when you go home. No, we were talking about Tagish Lake, and what he points out with Tagish Lake, so that's a meteoroid that landed, and it's primitive, but he claims that it probably had ice as it came through the atmosphere, and he thinks so that would suggest, and Tagish Lake I think has a short cosmic ray exposure age of about 1 million years or so, so that would suggest as a small body in space it had ice. But it has an orbit which comes from about 2.1 AU, so it's suggestive of coming from the asteroid belt, not a comet. So how does Tagish Lake fit into this story?
So if you want say the parent body of Tagish Lake, not the meteorite itself, to have readily available water ice, it's actually if you look at it's not up, but if you look at the slides for an evolution of a parent body, so don't just scrape it off the top desiccated part. Break apart about a few kilometers of the mantle that incorporates water ice in it as well.
But even if you did that, though, you still have to get it as a small body before you get it to the Earth.
Yes.
And it has to keep that ice, and it maybe has to keep that ice as long as its cosmic ray exposure age. If I'm understanding what Dan is saying.
And is the cosmic ray exposure age a few million years?
I think it's on that order. It's pretty short.
So then you go into a consideration of a few things. One, how big was that Tagish Lake small parent body? One thing. And the second thing is how oblique was its pole. We go back to the more analytic estimates from Norbert. You go back to these and you go, okay, so a lot of water ice could have been kept at a stable location just under the surface by having high obliquities, slower rotation rates, and things like that. So I don't really have a problem with that unless the parent body was very, very small. Something on the order of 100 meters, and I've ran these as well. I didn't show them because they're not interesting. Orders of 100 meters or so, they lose their ice very quickly. Timescales of 1 million or less than 1 million years.
Okay. We can talk more about it in a bit, but that's anyway. You get to fight with Dan now. So.
I mean, Dan is zooming in on you.
There's
So.
Dan right there. Fight away.
I can do it now.
The advantage I have in not being a theorist is I am unconstrained by the physics in my observations of what falls out of the sky.
Right, but I'm constrained by reality. So.
Well, for the longest time, people observed that continents moved around and were assured by geophysicists that would be impossible. So I've read the accounts of people collecting Tagish Lake. It indicates that there was ice coming out of the pieces of meteorites. I have gone and done the density and porosity of the frozen Tagish lakes, and those indicate that they still have ice in them. So I don't know how it's there, and I can't explain it. I just observe it.
So if you just wanted to be in that little piece of Tagish Lake meteorite, what you have is, if it's a little teeny bitty kind of thing, then the cooling time scale becomes much, much faster. So basically what you do is you heat and you cool almost immediately. You can think of it as you can think of it as, I don't know, maybe some comet astronomers would correct me, but you can think of it as like smaller ice grains and comas don't sublimate that quickly.
Okay.
We can ask questions in another. Or it could just be Canada in winter.
It could be. But there are actually warm parts of Canada. They're inside heated and places like that. And so that was the thing, is that chunks of Tagish Lake that were being collected that didn't have snow heaped upon them, you would put them on a table and they would end up in a puddle. And so that seemed to suggest there was ice inside. I have a question for you, Pascal. Phobos and Deimos, comets. It would be a wonderful thing if they were loaded with water. But the thing is that it would, of course, take a whole lot less porosity if the pore space was empty rather than loaded with water. Right. Just an observation.
Yeah, so that's a good point. The number I mentioned in terms of the maximum amount of water, which comes from the work we did with Yuta Tagaki, who's a student here, gives us a range of things because it's actually the model has three components. The interior model, it has the rock fraction, which itself can contain water of hydration. There's ice, and there's voids. So you vary the proportions of all three fractions while maintaining the bulk density, while constraining the bulk density, while keeping to the constraint of the bulk density, and then you can come up with these the ice contents, and the water content.
And the bulks you're using were 1.9 for Phobos and 1.5 for Deimos?
It's more like 1.87 for Phobos and then 1.4 for 7.
I'm rounding more than you are.
Yeah, okay.
So I had a question on this. How crazy is it to imagine to kind of reconcile the two and think that the impactor had a cometary origin?
Yeah. Well, exactly. So the impactor for the giant impact, right? You're talking about could have had a cometary origin. My understanding is that the orbital debris that results from a giant impact is normally dominated by the target material, which in the case of Mars could be water-rich.
That's generally not the case, actually. That's
really?
that's the other way around.
Okay, so the other way around, all right. So I thought the grazing impacts were dominated by the...
It depends on the impact configuration, but like for the moon, for instance,
Right.
the typical canonical type of impact generally places 90% impactor material, which was why there were so many concerns about isotopic similarities, etc.
So in other words, it does depend on the impact. I guess that was my point.
Yeah.
It's going to depend on the impact geometry as to what dominates the ultimate debris ring. So.
So I actually have a question.
Okay.
So you were talking about, so what drove you to the comet toroid origin for Phobos and Deimos was the starting point was their D-type or P-type classification. But as I showed in the slide, Deimos and Curry in 2014 showed that as you look at smaller and smaller asteroids, lower and lower masses, you get a plethora of P's and D's and B's and C's in the middle solar system, inner solar system, etc. So you don't necessarily have to bring something from way out there to be captured. It can be something that is in the main belt, which may serve somehow, and dynamicists come to the rescue as a way to help you catch what you want to catch. You first stop at the main belt and then continue.
Yeah. Okay. So first of all, we explored this possibility of a cometary connection, and incidentally, not because we want to identify Phobos and Deimos as cometary nuclei, which is sort of one of the ways of doing a connection, but just to show that because they're connected to D-type objects spectrally, and D-types are mostly found in the outer solar system, not exclusively, okay, but mostly in the outer solar system. And as it turns out, some D-types, like Don Quixote, are actually comet nuclei. All of a sudden, there's this interesting potential connection. I think it's a remote connection. It's more like, trying to explore the trade space of what Phobos and Deimos could possibly be. And in that trade space, you still have, the cometary option, which is sort of interesting. But I don't believe that it's likely. I don't think I wouldn't, expect
At that point, nothing really is likely anyway.
Well,
so.
exactly. Okay. So, it's just interesting as a possibility, and it should not be neglected.
Any other question? Yes, over there. Yeah.
This is about the tektites. Change the subject completely. presumably you're familiar that 4 or 5 years ago, John Watson came up with an idea that the Muay-Nong tektites were not impact-produced melts, but were in fact produced by flash heating from an airburst. So there is no crater to look for. Has that idea lost credibility?
So I think the tektite is produced by is provided from an impact melting because so first of all the composition of tektite are very similar to sedimentary rocks, and that's the most important thing. It's similar to sedimentary rock, so it should be from the earth material. And the second thing is that the water contents in tektite are depleted. It's low in water content. So
well, I think those would be consistent with Watson's idea. The point is the heat source is coming from a few kilometers up rather than subsurface during the compression stage of the impact. So it's a bit like Tunguska. The airburst happened, the thing disintegrated in the atmosphere, but an awful lot of heat and pressure got sent to the surface, and that melted the surface, including its water, or its water got folded in. Mm-hmm. So that's the gist of the theory. I was just wondering if an expert still thought that was likely.
Actually, I did not know about his work you mentioned. Maybe I ask you more about that. But actually, I think, from my opinion, I think tektite is from an impact melting and is associated with impact crater, not only Australia and other reason. Because based on geochemistry, you have composition.
That's right.
Yeah.
But I mean, Watson came up with his theory to address the question of where was the crater. But the other issue is that those tektites are spread all over Indonesia. They're so spread out, and they're not the flight type tektites. They're not aerodynamic.
So since Nyok and I worked on this together, you bring up a good point.
Derek.
Thank you. But here's the thing. As Nyok was pointing out, other tektite strewn fields are tied to known impact structures. And the other tektite strewn fields are much lower energy impact events. So nevertheless, there's melting, and you can connect those tektite strewn fields to small impact structures. Like the Reese crater has the Moldavites, the crater in Ghana has the tektites in Ghana. The Libyan desert glass has an impact structure now. So even for low energy tektites, you find a physical crater that has ejected them. It's just counterintuitive. I mean, impacts are so difficult sometimes to sort of intuit, but I can't imagine an airburst being able to eject that amount of tektites from the Indochina region all the way out to Australia, melting them all without actually having had contact with the surface. I mean, it just strikes me as being...
The theoretical modelers can do this. Right?
Yeah.
I'm being facetious now.
Yeah. Now, what's interesting is that 700,000 years ago when the impact took place, because that's the age of all the Australasian tektites, there was a glacial maximum. The sea levels were lower, and even if today it's a submerged impact structure, it might have been, in a continental platform at the time, and so, on land still.
It's okay.
There's also one at the back, maybe. But yeah, you have the microphone though.
Oh, I have the microphone. I get to ask my question. No, I was just going to follow up on that, and Dan and I were having a discussion while this was going on. Could it have been an ocean impact, or even like a shallow sea impact? Because I could see how that might give you a greater water content in the tektites, and also in terms of why we don't see the crater. I don't know of any submerged crater structures that were anywhere, right? Do we have any? Right, but these are all possible. Do we have anything confirmed? I mean, is it actually like something, well, that's the issue, is that, can you preserve, like how quickly by just subsurface, by sub-ocean erosion, do you get rid of a crater on even if it's a shallow impact, how quickly does that go away?
You're going to create a fractured crustal structure, and that would show up in your seismic lines and your geophysical surveys. The problem is, of course, that the people that do seismic lines and geophysical surveys very rarely publish them except under extreme duress.
Yeah. And it's hard to have very detailed, I mean, because we tried and are trying still to get detailed bathymetry of the Sea of South China Sea right at that location. But that logistical issue aside, there are known impact structures on the Arctic Ocean floor, for example. There's one that's known that's the highest latitude terrestrial impact structure, actually. It's higher latitude than Houghton Crater even. That's a submerged crater. And then there's Chicxulub, which at the time of the impact may or may not have been submerged. But
Chicxulub sort of a special case. The one I'm sorry, we're going to get a side discussion, but the one you mentioned, how big is it?
I forget. I don't know.
I mean,
I think the diameter could be about 20 kilometers.
Okay. Well, we can talk more. This is a fascinating topic. We should probably let other people ask questions.
Let's go to the back.
I have a question well, I have some information that I want to share. I was at the Royal Society meetings, and I got to hear the summary of the Philae lander measurements of the density structure of the head of Comet 67P Churyumov-Gerasimenko. And what they described, what Hermann Bonhart described, was that there is a fluffy layer a few meters thick, and then there's actually maybe 10 to 50 meters, I can't remember, but it was a fairly thick layer, 50-meter thick, very dense layer, and then below that was low density material. So I've just been wondering about its outgassing properties, how that might occur, but also how it might hide volatile material under the surface. And if we could get such a structure from either the outgassing properties or from some kind of formation history, it's just really intriguing that you could hide a lower density material. And then I've been reviewing the literature, and it's intriguing the work by Dan Cheers that followed Ben Rosaitis' work that suggested that if a body spins at a certain rate, that you actually can get a density buildup at the surface and kind of have a hollow inside. So I thought I'd bring this newest information about the measurements of Rosetta, a dust ice body, to the forefront and see if it sparks any interest.
Sounds great. That sounds consistent with sort of one of the latest models of Phobos' interior.
Also consistent with the fact that comets are crazy.
Yeah, well, yeah, okay.
All right, I think we are actually already dipping into the poster session. So thank you very much to everybody and participating in the discussion. And so now, in 5 minutes, the poster session is starting. Thank you.